5. Space debris. Space debris is orbital junk that is orbiting around the Earth at a very high speed. This debris can collide with space missions and damage satellites, space stations, and other space assets. The main sources of debris are A. Upper stages of rockets. B. Discarded rocket stages. C. Explosion of rockets or accidents in space. D. Anti-satellite demonstrations. E. Outdated satellites. There can be natural sources such as micro-meteorites. Kessler Syndrome. A scenario in which the density of low Earth orbit is so high that one accident can produce debris, causing more accidents, and thus, enhancing the likelihood of more collisions. This debris is a danger to the existing missions, as well as creates challenges for future missions. Steps to be taken. A. Keeping track of larger debris as part of space situational awareness. For example, Project Netra of ISRO. B. Ban on anti-satellite demonstrations. C. Separation of rocket stages at lower altitudes. D. Dedicated missions to destroy existing pieces of debris. For example, the Remove Debris mission led by the University of Surrey and the ELSADI mission by Astroscale. An international organization Interagency Space Debris Coordination Committee aims to coordinate efforts at a global scale to take care of space debris issues. ISRO is a member. Nuclear technology. Basics of nuclear technology. Nuclear technology in energy production. Radioactivity. Nuclear technology application, agriculture, medicine, space, industry, defense. Basic of nuclear technology. Atomic number refers to the number of protons. Atomic mass refers to the number of protons and neutrons. Isotopes are a family of elements that have the same atomic number. For example, carbon-12 and carbon-14, prosium, deuterium, and tritium, isotopes of hydrogen. Isobars are those elements that have the same atomic mass but the same atomic number. The protons in the nucleus are held together by a strong nuclear force. This force exists between the proton-proton, neutron-neutron, and proton-neutron. What is nuclear technology? Nuclear technology is the application of nuclear reactions. These are the reactions in which the nucleus or nuclear particles participate. There are nuclear reactions, which occur in nature such as nuclear fusion in stars and the decay of radioactive substances. There are nuclear reactions that can be conducted in a lab setup or an industrial setup. These reactions have applications in energy production, agriculture, medicine, space, etc. Nuclear technology in energy production. Energy production can occur in two ways: nuclear fission and nuclear fusion. Nuclear fission. In nuclear fission, a heavy nucleus such as uranium-235 is bombarded with neutrons so that a nucleus becomes unstable. Because of this instability, it disintegrates into lighter nuclei and produces a huge amount of energy. This energy can be calculated using Einstein's mass-energy equivalence equation, E is equal to mc2. Here c refers to the speed of light in a vacuum, 3*10⁸ ms. Nuclear fission reaction produces an excess of neutrons. These neutrons can continue the fission reaction. The reaction will grow exponentially in an uncontrolled manner. Such an uncontrolled chain reaction is the mechanism behind nuclear bombs. If we can absorb the excess of neutrons, the reaction becomes a controlled chain reaction, and energy output can be controlled. This is the mechanism behind the nuclear reactor. Nuclear reactors and their major components. Nuclear reactors utilize controlled fission to produce energy. It has the following major components. A. Fissile material, those which can undergo fission easily. There are two isotopes of uranium, U-235 and U-239. Plutonium-239 is also good fissile material. B. Control rods, these are used to absorb the excess neutrons. These are made of cadmium, boron. C. Moderators, they are used to slow down the speed of neutrons, and slower neutrons are better at causing fission. Water and heavy water are good moderators. D. Coolant, it maintains the temperature of the core by transporting the heat away from the core of the reactor. Often, moderators and coolants are the same. For example, water and heavy water are used as coolants. Liquid sodium is a good coolant, but not a good moderator. Nuclear fuel cycle. The nuclear fuel cycle signifies all the steps involved in nuclear energy production, as well as nuclear waste management. It comprises two parts, the front end and the back end. Front-end steps are the following: mining, milling, enrichment, fabrication process, and nuclear fission at the reactor. Mining refers to the extraction of uranium ore from a geographical location. Milling refers to the removal of impurities from the uranium ore by crushing and the use of physical and chemical separation methods. Enrichment refers to the removal of uranium-238 from the natural uranium using isotopic separation methods. It is to increase the concentration of the U-235 in the ore to 3 to 5%. Asterisk natural uranium has more than 99% of uranium-238 and less than 1% of uranium-235. In the fabrication process, enriched uranium is converted into pellets and embedded into a tube, which makes one fuel rod. Many fuel rods make one assembly, and many assemblies are used in the core of the reactor. Depending on the capacity, the reactor can produce energy for up to 4 to 7 years. The back-end step comprises of following. A. Interim storage. Nuclear waste is dangerous. It is removed from the core and is kept in a deep pool of water for a few years. B. Spent fuel reprocessing. We try to recover useful material, such as fissile material from nuclear waste. C. Final disposition. Nuclear waste is deposited in a permanent underground facility. Some countries do not use spent fuel reprocessing. Such a cycle is called the open nuclear fuel cycle. India's nuclear program is dependent upon spent fuel reprocessing, which is called a closed nuclear fuel cycle. The topics for the next class: nuclear fission, nuclear fusion, radioactivity.